All right, so good afternoon, everybody, and welcome to another program of Exploring by the Seat of Your Pants. If you're joining us for the first time today, we are all about bringing conservation, adventure, and science into classrooms around the world. And today is particularly special because today we continue our epic series in conjunction with the amazing folks at the Gairdner Foundation. So the Gairdner Awards celebrate some of the best health and biomedical researchers in the world every single year. Dozens of their laureates have gone on to win the Nobel Prize. In fact, we had a Nobel Prize winner join us last year who had just won his Nobel Prize the day before. So it's been a very special opportunity over the last couple of years to showcase and celebrate some really top-notch people joining us from around Canada and the world. Now, today for our program, we are bringing back Dr. Lewis Kay. He's joining us in Toronto today to talk about his amazing work unlocking the mysteries of life. So he works with the world of proteins, the building blocks of cells and of you, and uses some of the coolest high-tech toys in all of science to help uncover the mysteries within. So without further ado, I'm going to bring in Dr. Kay to join us to share a little bit of his story. And Lewis, thank you so much for being a part with us today.
Well, thank you very much for the opportunity and welcome folks from wherever you may be. So I want to begin my talk today by sort of asking a question. You think you want to be a scientist, and hopefully in the next 40 minutes or so, I'll convince you even more that you might want to be a scientist, or hopefully not less for certain. And I want to begin by asking a few questions. Now, normally what I would be doing is I would be giving a talk live and I would be able to see your responses. So you're just going to have to be able to answer the questions yourselves. How many of you are fascinated by math and science? How many of you find that despite your fascination of these subjects, that school science is too cookbook and you're wondering if science is in fact creative at all? And of course, how many of you would like to become scientists? And I'll ask you that at the end of my talk as well, and hopefully the number is not decreased. And finally, why am I asking so many stupid, silly questions? And the reason I'm doing that is because I have a couple of kids. They're past the high school stage now. One's 24 and one is 19. And my 24-year-old told me that when he was in high school, his favorite subject was English, because English, according to him, was way better. I presume he meant way better than science. And the reason is because he said that you could be super creative. You're given a blank page and you're told to write an essay or what have you. And of course, there's many different ways of doing it. You can just use your imagination and your creativity and your intelligence to put words down on paper. By contrast, he said that science is not taught in a creative manner. You get sort of questions like this. You take 20 mL of a solution, you add 5 milligrams of some compound, you stir the solution very vigorously for a few minutes or until your arm falls off, and then you add an additional 2 milligrams of a different compound, you watch the color change, and you write a report about it. And the fact is that many thousands of people have done precisely that experiment. So indeed, that type of science is not very creative. And that was his introduction to science and why he concluded that it wasn't very creative. So what I want to do today is to tell you that science can be, in fact, is super fun and very creative. And if you're curious and hardworking and clever, it just might be for you. Now let's come back to writing an essay that my son, at least when he was in high school, said was the sort of an element of creativity that was unsurpassed in the sciences. Now the process now may be creative, but just think about all the studying you had to do, all the practice, all the grammar that you had to learn, and all the words that you had to memorize before you could write that essay. So if you look at the definitive Oxford English Dictionary, and it's something like 20 volumes of the English language, there's about 175,000 words. But because of the fact that the words can be combined in a variety of different ways, there's almost 1 million different words that you can deal with. So before you write that essay, of course, you don't have to know 1 million words, but you have to know many tens of thousands of words, and you've been practicing your words all your life, presumably. And so you have a lot of experience. Now, in contrast, in chemistry, which is one of my fields, there's only 118 elements. So just think about how much simpler chemistry is than English. 118 versus 750,000. And let me try to take a different example. Let's look at, say, football. In an average playbook, there are, say, 30 run plays and 200 pass plays. This is in the NFL. And there's something like 5 or 6 variations on each play. So that makes over 1,000 plays. And of course, as a football player, you have to execute them at top speed. knowing that at some stage you're probably going to be getting slammed to the ground by somebody who weighs 300 pounds and is made of steel. So you've got many more rules of the game in football than you do in chemistry. And at the end, your reward is basically what you see here for this person on the left or this person on the right, basically on the ground in severe pain. By contrast, how many elements are there? There's only 100 and some. And some of these elements are, in fact, very precious and very beautiful. Take, for example, gold. Gold is an element that's worth a lot of money. Take sodium. Sodium reacts with oxygen to essentially produce some interesting products. In this particular case, you have burning of sodium. You have all sorts of different beautiful elements. And so it's actually fun to be able to look at the basic building blocks of chemistry. Some of them are precious metals, others react. But the point is that there's really a small number of these precious metals compared to the number of words or the number of plays there are for a football player. So maybe science really isn't so bad after all. Now, whatever you do takes a lot of training and a lot of hard work, whether you're a doctor or a lawyer, whether you're a taxi cab driver, and science is really no different. So the question is, what do I do? I'd like to introduce that and why people should care. Now, I'm at the crossroads between physics and biochemistry. So what I try to do as a physicist is I try to come up with ways based on the laws of chemistry and physics for solving problems in biology. I try to be super quantitative, very mathematical, very rigorous if I can be, but fundamentally I'm motivated by problems in biology. Now, I want to emphasize that despite the fact that I'm a scientist and very much into science, it's important to be well-rounded. For example, when I was in the high school environment, what I used to do in English class is take my math book, put it under my desk, and solve math problems. That was fine up until a point when I decided that I wanted to go to graduate school. I wrote exams, and I only scored 65% on the English section. So what I want to tell you today is that despite the fact that I'm emphasizing science, it's really super important that you focus on all subjects, because English in particular is the language of science, including mathematics, of course, but you have to convey your ideas in written English and in spoken English. So it's very important that you study all of your subjects, not just the sciences. Now, as scientists, what we try to do is we try to come up with patterns, or at least often I do, patterns that help simplify observations, and moreover, patterns that then allow me to make predictions from the observations that I have made to new experiments that I want to do. For example, if somebody were to ask you what's the sum of the first 100 numbers, you could simply sum the first number, 1 plus 2 plus 3, and so forth. But there's actually an easier way of doing that that involves looking for patterns. And I'll just illustrate that for the first 10 natural numbers, which are here, 1 through 10. If you want to sum them, you can do 1 plus 10 is 11, 2 plus 9 is 11, 3 plus 8 is 11, 4 plus 7 is 11, 5 plus 6 is 11. And so there's 11, but there's 5 of these 11. So 5 times 11 is 55. And you got that answer without actually individually summing every term. If you have the first 100 numbers, just sum 1 with 100, that's 101, 2 with 99, 3 with 98, and you're going to have 50 times 101. So you're going to get 5,050 as the sum. So you've got these neat sort of relationships which are based on patterns, and we as scientists like to find the patterns, whether they're patterns involved with numbers, whether they're patterns involved with certain aspects of biology or chemistry. And it's these sort of mathematical patterns which really fascinated me and pushed me into the mathematical sciences from a young age. So I wanted to be a mathematician or something like a mathematician when I was your age, but I still wanted to do something which I thought would be really, really, really super important. And just as a non-disclosure, I still haven't found what that might be. But in those days, when I was young, I wanted to cure cancer. So my real question was, how do I combine mathematics with cancer research? So here you have a gentleman on the left. He's a cancer researcher. You have a lady on the right. She's a mathematician. And I wanted to combine the best of both worlds to do something really important, but still to be able to build on my interest in mathematics. Now, I haven't really figured out how to bring mathematics into cancer research in a direct way, which would allow one to cure cancer. So I'm not going to be able to tell you about that today. But what I'd like to do is to tell you a little bit about the path that I took to becoming a scientist, combining my love of math and physics, shown here on the left, with how stuff works in the cell, shown here on the right. And this is an artist's rendition of the cell, and you can see that the cell is chock full of different molecules. Each one of these little blobs here in purple, in yellow, in white is a molecule, and these molecules are surrounded by other molecules, and I wanted to understand what's the molecular dance which gives rise to life. How is it the molecules are able to communicate with each other? I figured that you'd really have to be quite mathematical to be able to figure that one out. So math and physics would be involved. But fundamentally, we want to understand and apply these math and physics principles to questions in biology. So let me first describe the movers and shakers that are inside the cell before I can really explain to you what I do. So the global picture is shown here. We have a cell indicated here at the top. The cell is an enclosure. There's a biological membrane, if you like, or a gate that encloses the stuff inside of cells. And some of that stuff is going to be chromosomes, DNA, the blueprint for life. And of course, DNA contains the code, the genetic code, which codes ultimately for molecules which are called proteins. And I show here 4 different shapes, 4 different protein molecules that are going to be responsible for carrying out various biological functions in the human body. And that's what we want to understand, is how do those functions occur? And when there are misfunctions, like in disease, what is responsible for those misfunctions? And how can we change the misfunctions, convert the misfunctioned protein back into a functional one? Now, proteins play a wide spectrum of roles inside the cell. For example, antibodies are going to be proteins, and we know that antibodies are really important because antibodies are going to defend the body against foreign invaders, such as viruses and bacteria. Protein molecules can be cellular messengers. So if you imagine that you've got a cell and a membrane, which sort of separates the inside of the cell from the outside, you've got to get messages between the inside and the outside, and there are protein molecules that essentially convey the messages. Your muscles are made up of proteins. Your hair and nails are made up of proteins. There's proteins in the blood that carry oxygen to the various organs, which is obviously very important. There's proteins in brains and nerves that are involved in transmission of signals, for example. Proteins are also involved in speeding up reactions. Many of the chemical reactions in the body would take many, many days to occur if it were not for enzymes which speed them up, so that they can happen literally in seconds. And proteins also are going to build up other proteins. So proteins are construction workers, if you like. They build up protein molecules, but at the end of the function of these protein molecules, they have to chop them up before these spent molecules can aggregate and form, for example, neurodegenerative diseases. So proteins are pretty important. They don't do all of the work. They do a lot of the work. So you start with DNA, which is the code, convert to proteins, and then proteins are going to carry out a myriad of different activities in the cell. So given the importance of proteins for carrying out cellular function, let's look at them in a little bit more detail. And here I show a smorgasbord of very pretty pictures of proteins. You can see that they come in all sorts of different sizes, and they're made up of building blocks. So just like you have a necklace here, you can imagine a protein molecule is like this necklace, and a protein molecule is made up of 20 different building blocks, which are called amino acids. So you can think of them as these little entities here that are just colored in 20 different colors. And these different amino acids are going to attract or repel one another. There's going to be forces that either bring them together or that move them apart. That gives rise to for many of these protein molecules of a unique 3-dimensional structure. So these protein molecules are going to have a structure that is based on their composition. How many yellow beads are there? How many blue? How many green? It may be that greens are attracted to yellows but are repelled by reds. And that's going to impose certain geometric constraints on the shapes of these molecules. Some other protein molecules, in fact, really have no shapes. They convert between all sorts of different shapes in a very rapid manner, sort of like various spaghetti particles on a plate. If you can sort of think about these random spaghettis that are on a plate, you've got protein molecules, some of them, that are going to assume random conformations, random shapes that are going to be changing all the time. And so let me just show you a few of these shapes. So this is a protein called calmodulin, which is a very important protein in the body. And this is one shape that calmodulin can assume. But when calmodulin binds its targets, and shown here is a red target, the shape of this molecule changes. So molecules respond to their environment through interacting with other molecules in the environment. It causes very significant changes in their three-dimensional shapes. This is an antibody molecule where you have this region here and this region here that recognizes foreign species and is very important in the host immune response. And you have other molecules. For example, some are going to print money, if you like. In the cell, that money is something called ATP. ATP is an energy source, and these printers are made up of protein molecules. They're molecular machines, just like we can have machines in a car engine is a machine. We can have molecular machines that move about, and in so doing, they generate ATP in the case shown here in A. Other protein molecules in machines may steer a cell towards food or away from danger. So these protein complexes are essentially the steering wheels of the cell. So proteins can be machines as well. They can also serve as gates, allowing various ions in this particular case to pass through a cell membrane. So just like gates can be closed in this case or open, so too proteins can be closed or open to either not allow or allow other molecules to come into a cell and therefore carry out a function. And protein molecules can also read and follow instructions. For example, in the construction of other protein molecules following the code of DNA. So protein molecules, again, carry out a myriad of different functions. Here's one of my favorite protein molecules. It's actually a garbage can. This big thing is a garbage can. It's much bigger than the first protein that I showed you called calmodulin. And this garbage can is going to chop up proteins that are no longer needed by the cell before they can do any damage. So this is a very important molecule indeed. Now, protein molecules are not static, and we really can't capture how they work from a single picture. So what I try to do is to understand how the pictures change in time. And you might say, well, why does this matter? And so let me illustrate that. Again, I want to focus on this engine here. This is a macroscopic machine. It's the sort of machines that we come in contact with every day. But the machines that I come in contact with every day are these microscopic machines, these tiny machines that are just as complicated as your car engine and are moving about just like your car engine is. And we have to understand what those movements are all about. Now, a single picture doesn't capture function, not for a machine like a car engine and not for a molecule. And let me just illustrate that in the following way. Suppose that you've never seen a baby before, and I show you these two pictures of babies. You could make some conclusion about what a baby looks like, right? You would say babies always wear something that is green. You would say that babies are either always happy or always eating. And of course, you really haven't captured the true essence of baby yet, because babies are not always wearing green and they're not always good feeders. You can see that illustrated here for this baby. And babies are not always happy. Here you have a baby that is crying. So what you really need to describe a baby is a whole bunch of pictures. You need a movie picture, essentially, and it's the sum of all the parts which give you much more information about what a baby is. And just like multiple states are needed to understand babies, so too with proteins. For example, if we have this molecule here, which is an enzyme, we have a small molecule here. This is a protein molecule that is going to chop this blue molecule into two. So it arranges itself in a manner which allows the reaction to occur. And now you can see the two blue pieces moving away. So there's dynamics, which is responsible for function. But proteins don't need an excuse to be dynamic. They're dynamic all by themselves. So if you imagine a protein molecule, and protein molecules are essentially beads on a string, and the beads are made up of atoms. Each bead is called an amino acid, and there's roughly 20 different amino acids. So 20 different colors of the beads. These amino acids are in general going to be arranged in a three-dimensional representation, which gives the protein molecule its structure. And you can see that the structure of the protein is made up of these purple helices and these yellow strands. This is one molecule, but remember, in the cell there would be many, many molecules. And all of these molecules are going to be bashing into one another, water molecules, other protein molecules, and they're going to be exchanging energy. So if you imagine you have a protein molecule, it's being bombarded with water molecules. The energy from the water molecules is conveyed to the protein molecule. And if the energy is conveyed in just the right way, it's going to result in a change in the structure of the protein molecule, which is going to lead to a particular function. So it's not just the three-dimensional static structure that's important, but rather it's the dance of the protein molecule. The dance of the protein molecule that comes about by virtue of the fact that these molecules are going to be surrounded by other molecules. And it's this dance that I try to understand. So how do I do that? Well, the technique that I use involves magnetism. And you might think that magnetism is a weird way to understand how these tiny molecules are going to dance. So a natural question is, why do I choose magnetism to understand how molecules inside the cell behave? What's so special about magnetism? And this is the answer. This is an answer from a famous physicist by the name of Dave Barry. Magnetism is one of the 6 fundamental forces of the universe. That's pretty important, with the other 5 being gravity, duct tape, winding, remote control, and the force that pulls dogs towards the groins of strangers. So we're going to focus on the first of the 6 fundamental forces, and that is magnetism. And let me just remind you of something that, of course, you all know. You all know that if we have a typical magnet, the sort of magnet that you might put on a fridge, for example, there's a north pole, there's a south pole, and north poles and south poles are attracted to each other. North poles and north poles are repelled, and south poles and south poles are also going to be repelled. So that's basically what you have to understand. But still, how does a magnet have to deal with understanding the dance of these molecules? And so let me actually come back to the molecules that we've been focused on. These are protein molecules. Here's a schematic of a protein molecule. It's a 3-dimensional shape, for example. And these molecules are made up of amino acids, and the amino acids are made up of atoms. And these atoms are carbon and hydrogen and nitrogen and oxygen and sulfur. Those are the basic atoms, the basic elements that are going to make up of protein molecules. Now, it turns out that if we look at a realistic representation of a protein, shown here in the bottom right panel, and if we focus, we zoom in, you can see these white little dashes. Those are hydrogens. And every one of those hydrogens is going to be a little bar magnet. Now, it's a bit of a different magnet than the sort that you put on your fridge because it's so tiny. And we have to understand the properties of the magnet using a field of physics called quantum mechanics. But it works more or less the same as the sort of magnets that you're used to. So the point is that the protein has hydrogens and carbons and nitrogens. These too can be little bar magnets. So the protein is made up of little bar magnets. And so if we can learn something about the magnetic fields that these little bar magnets in the protein are given off, we might be able to learn something about the protein itself. And that's why I deal with magnetic fields. Let me try to explain to you what it is that I do. So what I do is I get a big sack of money in the form of a grant from the government, and I buy a giant magnetic field. This would be a magnetic field that would be 500,000 times bigger than the Earth's magnetic field. And I'm going to denote that by the big N here and the big S here, okay? There's a north and a south pole. And then I'm going to take my protein molecule and I'm going to put it between these poles. So inside the big magnetic field that I've spent millions of dollars on. Now, the protein molecule is made up of little bar magnets. And these little bar magnets are going to obey physics, which means that the south pole of the little bar magnet, the little atom attached to the protein, faces towards the north. And the north pole faces towards the south of my big magnet. That's the lowest energy position. And so that's what's going to happen for all of the bar magnets that make up my protein. And then I'm going to do something. I'm going to basically apply magnetic energy into the system. Let's suppose we had the following. Suppose we had a punching bag. So you know these punching bags are these kind of balloon things that are upright. And then you come home after a rotten day in school when you only got 97% on your test and you can't understand why you didn't get 100, and you punch your punching bag, right? So what happens is the punching bag moves towards the ground. You've supplied energy into the punching bag. The punching bag is now in a high energy state, and then the punching bag loses the energy and comes back to the low energy state. And that's what we're going to do in NMR. We're going to use our little bar magnets, the atoms, as punching bags. We apply energy, not with our fists, but magnetic energy. That energy is absorbed by these little bar magnets, and it changes their orientation with respect to the big magnetic field. You can see this little bar magnet has swung around. Red was up, and now it's down. And then we watch the little bar magnets come back to the normal low energy position. And that gives us information about the three-dimensional structure, about how the structure is changing over time. So we can get the dance of the whole molecule by watching how the individual pieces, the individual atoms respond to our, if you like, punches, the energy that we supply. So what I do is I develop the math and the physics. I decide how I want to punch these little bar magnets. Big punches, small punches, how often I want to punch them, so that I can tease out as much information as I can about the three-dimensional shape and how it changes in time. And I want to just give you one little example, leave you with the following example. This is one molecule that we've been studying for many years now in the lab. It's a molecule that is involved in a neurodegenerative disease, which leads to death. Now, this molecule is actually made up of 6 copies. Each copy has 800 beads, so 800 amino acids. And you can see that there are 2 forms of the molecule. So up here is form 1, down here is form 2. And you can see that the difference really is that these blue arms move above the plane of the rest of the molecule, depicted here. Here we have the arm, which is by the side in this structure, and it's above in this structure. And these arms are very important, just like your arms are very important, because these arms are how this molecule interacts with its surroundings. And so if we change these arms, we change how it interacts. Now, it turns out that a single error, 1 amino acid of the 800, 1 error, 1 change in the color of the bead is enough to cause the arms, which normally should be down, to go up. If you had an exam and you had 800 questions and you got 799 right, that would be pretty good. But in this business, getting 1 out of 800 wrong is enough to cause a very severe neurodegenerative disease and death in patients. And what we've done in the lab is we figured out how to essentially take these diseased proteins where the arms are up, as shown here, and convince these arms to go down by studying the dynamics of the various pieces that comprise the protein, or if you like, the various pieces of the engine. So by knowing how the various pieces of this microscopic engine work, we're able to regulate the up and the down positions of the arms in such a way that we can push things back into the proper position, at least at the test tube. And of course, one has to demonstrate that ultimately in living systems as well. So I want to conclude by saying something that I started with, and that is that science is creative. Learning the rules is very hard, as it is for any game. But playing the game of science is ultimately extremely rewarding because it's incredibly creative. Don't get discouraged. In chemistry, there's only 118 elements. And if you've taken physics, there's only 5 or 6 formulas that you have to know. And in physics, basically everything is ultimately equal to 0. So it's even simpler than that. But in English, you've got 750,000 words. Choose your passion, listen to your teachers, but not too much. I remember when I was in high school and the teacher used to go to the board and the teacher would say, okay, to solve this type of problem, this is what you do. Step 1, step 2, step 3. There were always so many different steps. And I like to solve things my own way. And I think that's really important because each and every one of you can solve a problem in your own unique way that is different from everybody else. And it may be that the way that you look at a really important problem is going to provide an answer to it in a manner that nobody else has been able to figure out. So you can uniquely figure out answers to your questions in your own ways. And above all, don't let anybody tell you that you can't, because of course you can. Good luck.
Thank you so much, Lewis. If you want to come out of screen share now so you can see us again, have a bit of a conversation, that would be spectacular. I'll give you a second to do that. YouTube classes, if you guys want to share questions in the chat, please do. I had some written ones in advance of the program too. Ms. Bull, I will come to you guys live in a second, but I'll start off with a softball one for Lewis here as he's coming to stuff. I'll get rid of the screen share there. There we go. Perfect. Lewis, one of the questions we always get in these programs is if you have a favorite part of your job. You highlighted a lot of different roles that you get to play, a lot of different collaborations you get to have. Is there anything that stands out on a day-by-day basis that you get to do?
Yeah, I get to have fun every day. I do exactly what I want. I develop experiments. I help my students every day. Every day we have a problem or 10, and we try to solve them. Now, we don't solve 10 problems a day. In fact, we don't often solve one problem a day. We solve tiny little problems, but that's enough to give me enough of a impetus to get up the next day and to continue on. So I would say it's the sense of adventure. It's the sense that I don't know what's going to happen in any given day that really provides me with the motivation to go forth.
Yeah, fantastic. Ms. Ballsglass, Goddard, if you guys want to come on in, you're good to go for a question. Hey.
Hey, Jesse, I just wondered if you could give us more information about that garbage can protein. I wanted to know its name and maybe a little bit more about its function.
Fantastic.
Right. So this garbage can protein is called the proteasome. So the proteasome is something called the protease. And the reason it's called the protease is because it chops up other proteins. So if you imagine a barrel, and this thing is a barrel, and you have stuff that comes in the top or the bottom, is then going to be chopped up, and then it's going to be released. So the question is, how does this barrel interact with other molecules? Other molecules that are diseased, for example, have to get inside the barrel, but healthy molecules that are still functional, you don't want to get inside the barrel because they're going to be chopped up then. So how is it that molecules can go in, some, and some cannot go in? What is the level of regulation? And how is it that if you imagine a barrel, you have stuff on the top of the barrel, stuff on the bottom, how is it that the regulators of the barrel, which are all on the top and the bottom, so if you imagine a regulator of a barrel is another protein molecule that is sort of like the garbage, the top is like, you know, the top that you put on a garbage can. What do they call that?
Lid.
A lid, yes, it's a lid. There are protein lids on the top and the bottom. And the thing is that when you get a lid on the top or the bottom, it communicates with the rest of the garbage can. And so one of the questions we wanted to ask is how that communication occurs. And another question we wanted to ask, because that communication is occurring over, you know, a big distance. So how is it that when the lid binds to the garbage can, the rest of the molecule knows? And this garbage can is going to chop things up. So that's very important for a normal cell. But if you imagine a cancer cell is going to be reproducing very, very rapidly, replicating very rapidly. Mitosis is happening very, very quickly. And so what you want to do, because of the fact that this cancer cell is going to be so metabolically active, it's producing proteins left, right, and center, because it's going to be carrying out division all the time. So it needs really to be very active. Now, if it's producing proteins left, right, and center, it stands to reason that some of those proteins are going to get old. And if they're going to get old, they could clump up and really kill the cancer cell. But the problem is you have this giant garbage can, which is going to take the proteins in and chop them up. So can you come up with a drug that can bind to the garbage can and it can slow it down so that cells that are metabolizing so quickly, like a cancer cell, essentially can no longer function because the damaged cells can't be chopped up fast enough. The thing clogs up and the cancer cells die. And so we've been working on ways that we can produce these small molecules. Where do they interact with? How do they control these garbage cans? Because there's a whole relay of information, a whole highway, if you like, that you can touch the molecule in one site and another site located at the other end can be affected. So how can we play the game where we touch a molecule at one end and affect its function at another end? And that, of course, has important implications for, as I mentioned, drugs for various diseases like cancer.
Louis, I've got to say, it's both exciting. I mean, I'm smiling listening to how enthusiastic you are about all this, but I never thought in my life I'd hear the phrase so passionately, how do we control the garbage cans? That's an unexpected joy of Exploring by the Seat of Your Pants podcast.
Well, another garbage strike in Toronto, and
Yeah.
you realize how passionate people are about garbage.
So in the last year and a bit, there's been these really breathless, excited articles in Science and Nature, which are two publications that are not necessarily used to breathless, excited articles, about something called AlphaFold 2, so the capacity of artificial intelligence to sort of dictate and understand protein structure in a way that was previously not possible before. Can you speak a little to this and how artificial intelligence is impacting the field, or specifically the work that you're doing?
Absolutely. So you always want to know what something looks like. So you always want to have a three-dimensional picture of that. And traditionally, the approaches for getting these three-dimensional pictures have been to use experiments. Experiments like the one that I develop that involves magnetic fields, experiments that involve X-rays, or experiments that involve electrons. So these are experiments that you actually have to do that can take large periods of time and very competent scientists to be able to get out a three-dimensional image. Now, we have a large number of three-dimensional images of molecules, so it stands to reason that if we can learn the rules by which these molecules fold up, and this is where artificial intelligence and computation comes in, then we can take these rules and we can apply them to other systems, other proteins for which we don't have a structure, and hopefully get accurate structures. And this AlphaFold is one such program that essentially is able to produce really very accurately three-dimensional structures. Now, therefore, you say, well, that's great. That means that all of these scientists like me are just out of a job because we now have these computers that can work a lot harder than I can without ever complaining, without, giving them much in terms of food, except for a little bit of electricity, and they produce all of these wonderful structures. But here's the thing. These structures by themselves don't tell us how things work. We've got to understand how these structures change. And what AlphaFold cannot do now, or no program, is basically understand the molecular dance. So they can give me the structure of something, but how it changes, which is responsible both for its function and its misfunction, these programs cannot tell me. So I am in as much business now as I ever was, and even more so because I don't have to worry about this tedious, let's just get a structure. I can go to AlphaFold, I can get my structure, and then I can start thinking right away without having to do the 6 or 8 or 10 months worth of work to get the three-dimensional structure before I can begin. So it actually accelerates my work rather than hinders it. So it's a win-win situation.
Spectacular. So the breathless articles were right. And I mean, this is the exciting thing with scientific development, is that we're starting to find in biomedical and health fields, again, we've been featuring a lot of Gardner scientists over the last few days, or laureates that work all across the world. And the speed of technological development and the sort of enhanced capacity to do work quickly without dealing with some of that sort of mundane work to get there is been spectacular, and everyone's been featuring that in all our broadcasts. I'm really glad you highlighted that as well. Louis, time flies and you're having fun. I'm going to go back to our live class. YouTubers, you guys can email us questions after the fact if you're keen. Ms. Ball, if you have one more question before we wrap up, you are welcome into the program. Hey.
Thanks again, Jesse. So we've talked about the garbage can protein, and you mentioned a bit about the one related to dementia. I just wondered if you had, I don't know, your top 3 favorite proteins or that people should know more about.
Lay
Oh,
it down for us, Lewis.
there's a lot of proteins. What I would recommend actually is just sort of learning the general aspects of proteins. What is it that proteins do? What is it they don't do very well? What are the sort of themes that are responsible for various diseases? Like in neurodegenerative diseases, we have these proteins that are called chaperones. These proteins recognize other protein molecules that are in danger. They may hold on to them. They may unfold them. If you've got a protein molecule that is folded in the wrong way, so it can't carry out its function, and moreover, a sticky end of that folded protein is now available to interact with a sticky end of another protein to give you a glob, which causes disease. These chaperones are going to unfold the proteins and prevent them from essentially interacting with other molecules, allow them to give them time, another chance to fold up properly. So I would say I don't have a favorite protein. I just have marvel at what these protein molecules can do, how they function, and why it is that their function really keeps us healthy. So I would recommend for people that are interested in this sort of thing that rather than focus on one or two, that you focus on general classes and try to understand the specific nature of these general classes and the wonderful ways in which they're able to maintain a living system.
It's so nice for me as a biologist by background, because the question that we get most often in our programs, especially conservation themed, is, do you have a favorite animal? So I'm glad we got the protein version of this today. And you stuck with our traditional answer from biologists too, which is, no way, there's no way I could pick one. They're all so cool. The way they interact is the best part of the ecology. Oh dear, it's very funny for me. Lewis, this has been a lot of fun. Thank you so much for joining us as part of this series.
Pleasure.
And again, you're welcome back anytime. Every time we do a Gardner series in any particular month, you're like top of the list for everyone that we get in. So exciting to feature proteins today. If people are keen, they can check out Gardner.org at Gardner Awards for more on you and your work. You're all over the web if people want to look up more about your specific lab and the things that you do. And as always, all our programs are on our YouTube channel. So if people want to check out this one again, any of the others in our Gardner series, it's very easy to do so there. Lewis, I know you've joined us before, so you know how we wrap up the broadcast. I'm going to bring in Miss Ball's class to say a big thank you and farewell with me, but we really appreciate you joining us today. Have a nice